So imagine you have just invented a completely groundbreaking new product in a lab.
Oh, that is the dream, right?
Exactly. Maybe it is this revolutionary new medicine or a new type of biodegradable plastic or even a completely clean biofuel.
And you have it working perfectly.
Right, but it is only working perfectly in a tiny, sterile test tube. You are literally holding, a few milliliters of the future right there in your hand. But then you hit this massive looming question.
How do you actually scale that up?
Yes. How do you go from a tiny test tube to a massive multi-million-dollar factory without going totally bankrupt if you make a single mistake?
I mean, that really is the ultimate cliffhanger for any new discovery. Because going from a few milliliters on a lab bench to a commercial scale it is incredibly perilous.
Everything just changes, right?
Exactly. The physics change, the biology behaves totally differently at a large scale, and the costs just grow exponentially.
Well, that is exactly what we are exploring today. I am your storyteller, Stellar, and we are jumping into part 1 of an introduction to bioprocess design.
It is such a crucial topic to unpack.
It really is. And to help us decode the science today, joining me for this deep dive is our expert technologist, Dr. Rama Yusvana. He is a chartered biologist of the UK Royal Society of Biology and a senior lecturer at the University Tun Hussein on Malaysia, or UTHM.
Thank you. It is genuinely great to be here to talk about this.
And I should actually mention, for the second-year university students tuning in, this deep dive is an introductory preparation class for students taking Chemical Engineering Technology Simulation at UTHM's Faculty of Engineering Technology.
Right. This is the primer before they get into the actual hands-on simulation class using SuperPro Designer, which is an industry standard tool.
So our main mission today is to understand how engineers essentially build and break entire virtual factories in a computer. But before we get to the software, we need to define the core concept. What exactly is bioprocess design?
Well, simply put, it is the engineering discipline of taking a biological idea and figuring out how to manufacture it on a commercial scale safely and profitably.
So taking that test tube and turning it into a working factory.
Exactly. And the diversity of what we are trying to manufacture is staggering. We model facilities that produce all sorts of bioproducts.
What kind of categories are we talking about?
Oh, there are many. You have organic acids used in the food industry, massive volumes of industrial enzymes, and delicate antibiotics.
Okay, so food processing and medicine.
Right. But also amino acids, advanced biofuels made from agricultural waste, biopolymers, and even microbial biomass products.
Wait, microbial biomass? Like what exactly?
Like baker's yeast. That is a massive industrial bioproduct. And every single one of those requires a completely different biological environment and physical infrastructure.
That is just a wild range of products. And honestly, just thinking about modeling a factory that produces any one of those sounds, well, overwhelmingly complex.
It is.
Like if I am an engineer sitting down at a computer screen, how do I even begin to map out miles of piping and hundreds of reactions without completely losing my mind?
Yeah, cognitive overload is a very real danger here. If you try to look at every single valve and pipe at once, it is just visual noise.
I would just freeze up immediately.
Exactly. So to stop engineers from getting overwhelmed, the simulation software organizes this massive complexity into 3 distinct manageable levels.
Okay, 3 levels. Let us break those down.
Sure. Level 1 is the flow sheet, level 2 is unit procedures, and level 3 is operations.
Thinking about this 3-level architecture, it actually sounds a lot like the logistics of running a massive high-end restaurant.
A restaurant is actually a great way to frame it. How would you map that out?
Well, level 1, the flow sheet, would just be the big picture, like the entire restaurant floor plan.
Right, the macro view.
Exactly. It shows where the raw ingredients enter the loading dock, how they flow into the kitchen, and how the cooked food leaves through the dining room, just the flow of materials.
Spot on. And then level 2.
Level 2, the unit procedure, would zoom in on a specific workstation, like the baking station or the industrial oven. And then level 3, the operations, are those highly granular step-by-step tasks within that station, like open oven door, preheat to 400 degrees, or beak for 20 minutes.
That captures the architecture perfectly. You have to maintain that big picture of material flows to ensure the factory makes sense, but you also need to zoom all the way down to the physics of a single action.
It makes a lot of sense when you put it that way.
Let us look at a real industrial example from the sources, the production of beta-galactosidase.
Okay, what is that used for?
It is an intracellular enzyme produced by E. coli bacteria, and the dairy industry uses it heavily to manufacture lactose-free milk.
Intracellular meaning the bacteria are producing this enzyme inside their own cell wall, so you eventually have to break them open to get it out.
Exactly. The process of growing them, harvesting them, breaking them open, and purifying the enzyme requires a massive sequence of machinery.
I can imagine.
The digital flow sheet for this is sprawling, so engineers use strict color coding to group the unit procedures visually.
Oh, smart. How is it coded?
The fermentation phase, where the biological growth happens inside the bioreactors, is coded black.
Okay, black for fermentation.
Then primary recovery, which involves breaking the cells and doing the rough separation, is coded blue. And finally, purification, the highly sensitive final refining step, is green.
So it acts as a visual anchor. Plus, I read that the software has a tool called the Navigator.
Yes, the Navigator is essential.
If you play video games, you can think of it like the mini map in the corner of your screen. It gives you a thumbnail overview of the entire factory floor.
Right, so you can instantly jump between the black section and the green section. It keeps the modeler from getting totally lost while staring at the math for a single chromatography column.
You design the macro, but you calculate the micro.
Precisely.
You know, before we move on, let us just do a quick recap. So far, we have learned that bioprocess design is how we safely scale up lab ideas into commercial products. And engineers build digital twins using a 3-level architecture to map out the physical layout without getting overwhelmed.
Yes, starting with a strong foundation is key.
Definitely. And actually, for any of you listening who are hooked by this, there is an amazing opportunity here. You can actually do master or PhD research studies with our expert or his colleagues at UTHM on various topics in biotechnology or bio-based systems.
We absolutely welcome curious minds. There is always more groundbreaking research to do.
It is such a cool field to get into. But so far, we have really only been talking about spatial layout, right? Where things are and how they connect physically.
That is true. But a real factory does not just exist in space. It operates in time.
Right. The physical blueprint is useless if the clockwork is broken. So we have to transition from physical layout to temporal logistics.
And time is arguably the most critical variable in the entire simulation. When we look at logistics, processes generally fall into 2 categories: continuous and batch.
Continuous processes are exactly what they sound like, I assume.
Exactly. Think of an industrial wastewater treatment plant or a massive petroleum refinery. The raw material flows in constantly and the product flows out constantly, 24/7, without stopping.
But biological processes like making our lactose-free enzymes or even brewing beer, they usually rely on batch processing, right?
Yes, they happen in distinct, isolated cycles. You load the ingredients into a tank, let the reaction run, empty it, clean it thoroughly, and then start the whole cycle over from scratch.
And that start and stop nature has to make the timeline incredibly tricky.
It is a scheduling nightmare. Take a large-scale industrial brewery. On paper, the batch steps seem straightforward. First, you grind the barley malt and corn grits.
Okay, makes sense.
Then you mash them with hot water to extract sugars. Next, you boil that sweet mixture with hops. Finally, you cool it down, add yeast, and let it ferment and condition.
But when you map those steps onto a timeline, problems start to emerge, don't they?
Massive problems. To visualize this, the software generates an equipment occupancy chart.
Which is basically a Gantt chart, right? A timeline with colored blocks showing exactly how long a batch occupies a specific piece of equipment.
Exactly. And when you look at that chart for the brewery, a huge bottleneck becomes obvious immediately. Grinding the malt might take a few hours. Boiling the hops takes a few hours.
Okay.
But the conditioning tank, where the beer sits and develops its flavor, takes a full week. That one tank becomes the ultimate choke point.
Wait, if the conditioning tank takes a week, but the mashing and boiling tanks only take a few hours, does the entire rest of the multi-million-dollar factory just sit there, idle?
In a poorly designed facility, yes. That is exactly what happens.
Doing absolutely nothing.
Right. You spend millions on giant stainless steel boiling kettles, and they are sitting empty 80% of the time because there is nowhere to send the liquid.
Oh, wow. That is a terrible investment.
Which is why you build the digital twin. The simulation exposes this temporal flaw visually and then lets you test a solution known as staggered mode.
Staggered mode. I am guessing that means you selectively duplicate the equipment causing the traffic jam.
Precisely. You do not build a second complete factory. You just add multiple identical conditioning tanks that operate out of phase with each other.
So if you have, say, 4 conditioning tanks, you stagger their start times.
Exactly. So by the time your boiling kettle finishes a new batch, tank number 1 might be full, but tank number 2 is empty and waiting for it.
You essentially turn a clunky stop-and-go batch process into a smooth, continuous flow.
And the impact is profound. In one biopharmaceutical case study for monoclonal antibodies, the initial batch cycle time was 14 days.
Okay, 2 weeks.
But by adding staggered bioreactors, they slashed the cycle time down to just 3.5 days.
Wait, from 14 days to 3.5 days?
Yes. That is the magic of debottlenecking in the virtual world before you buy a single piece of steel.
I mean, let's just recap that briefly. We use Gantt charts to expose where the factory is essentially taking a nap, and then we stagger equipment to keep things moving. And cutting a batch from 14 days to 3.5 days is not just a scheduling trick. That fundamentally alters the economics, right?
Oh, absolutely. Because time literally is money.
Yeah.
Shorter cycle times mean you push dozens of extra batches through the same facility every year,
More batches mean vastly more product to sell.
which transforms the profit margins. But calculating profit also means understanding the immense costs of building and running the facility in the first place.
Which brings us to the next major function of the digital twin, the money.
Yes, the simulation generates rigorous economic evaluation reports. It breaks the finances down into two main buckets, CapEx and OpEx.
CapEx stands for capital expenditure, or direct fixed capital, right?
Yeah.
The massive upfront cost to build the place.
Exactly. And OpEx stands for operating expenditure, the day-to-day cost to keep the lights on, buy materials, pay staff, and manage waste.
Let us talk about CapEx first, because there is a deeply counterintuitive insight here. If someone asked me what the most expensive part of building an antibody factory is, I would definitely guess it is the giant, highly advanced bioreactors.
Most people would. But the direct fixed capital is often 10 times larger than the actual cost of the manufacturing equipment itself.
A 10x multiplier, that is wild.
Machines are expensive, yes. But installing them requires infrastructure that is unimaginably complex.
What makes it so expensive?
You need miles of specialized high-purity piping that can be sterilized with pressurized steam. You need stringent clean room environments with massive HVAC systems to filter the air perfectly.
Oh, right, because any contamination ruins the whole batch.
Exactly. Plus complex instrumentation, automated valves, and rigorous regulatory validation. The shell that houses the equipment costs 10 times more than the equipment.
That is staggering, and the economic surprises keep coming when we look at OpEx. You would assume the biggest drain on cash would be specialized raw materials or, salaries for the PhD scientists.
But in many biopharma processes, the dominating OpEx cost is actually consumables.
Consumables being the items that are used once or maybe a few times and then totally replaced.
Right. We're talking about highly engineered, single-use disposable bioreactor bags, specialized membrane filters, and incredibly expensive chromatography resins.
It honestly reminds me of the trap of buying a cheap home printer.
Oh, that is a great analogy.
Yeah, like you buy the printer thinking you got an amazing deal, but over the next 3 years, you go completely broke buying those proprietary ink cartridges over and over again. The hardware is a one-time hit, but the consumables bleed you dry.
The printer ink analogy is perfect for biopharma. But you might ask, if the consumables are so expensive, why do engineers choose to use them at all?
Right, why use a massive disposable plastic bag inside a bioreactor instead of just a bare stainless steel tank?
The digital twin helps answer this by balancing OpEx against time. If you use a bare tank, you have to spend days cleaning it, sterilizing it with steam, and validating that it's perfectly clean before the next batch.
Which costs water, energy, and precious time.
Exactly. But if you use a sterile disposable bag, you just pull the used bag out, drop a new one in, and you are ready for the next batch immediately.
So you pay a high premium for the consumable bag, but you gain back days of manufacturing time.
Right. It is a complex economic trade-off. Identifying those hidden costs and balancing them during the digital simulation phase is crucial. Because once the physical plant is built, you are locked into those operational expenses for decades.
Which raises an inevitable question. If the upfront building costs are astronomical and the day-to-day consumables are bleeding the budget, how do engineers fight back? How do they squeeze efficiency out of the margins to save every last penny?
They fight back using optimization techniques that would be almost impossible to calculate manually. Two of the most powerful are virtual energy recovery and material recycling.
Let us look at the energy side first, because heating and cooling must be massive utility grains.
Huge. Take a continuous operation like a corn refinery. You have raw materials that need to be boiled and finished products that need to be chilled.
Creating all that steam, And running industrial chillers takes an unbelievable amount of electricity.
Traditionally, to save money, an engineer would try to route a pipe of hot liquid next to a pipe of cold liquid, using a heat exchanger so the hot stream naturally warms up the cold stream.
But drawing that complex spaghetti of piping across a massive factory floor sounds like a logistical nightmare.
It is. But inside the digital twin, you have a virtual energy recovery tool. Engineers do not even have to manually figure out the physical routing of the pipes in the early design phase.
They just let the software handle it.
Exactly. The software looks at the thermodynamics of the entire factory at once. You just tell it to look for logical matches.
So if you have hot syrup at 70 degrees Celsius that needs cooling and incoming cold wash water across the building that needs heating,
the software virtually swaps the heat between those two streams.
wow.
It instantly runs the thermodynamics and calculates exactly how much money you would save on your utility bill if you connected them.
It tells you if the energy savings justify the cost of actually building that specific pipe without you having to manually map it all out first. That is such an elegant way to slash the OpEx.
It is engineering foresight at its best. Now, what about saving on the raw materials themselves? We see a brilliant example of this in the continuous production of baker's yeast.
Okay, the recycling loop.
Right. To save millions of gallons of water and boost yield, engineers recycle the liquid waste stream that exits the centrifuge, piping it right back into the initial fermentation tank.
Recycling wastewater sounds great for efficiency, but biologically it introduces a major catch, right? Because when you recycle that broth, the yeast are essentially living in their own recycled water.
Yes. And over time, inhibitory metabolites begin to build up.
Metabolites being the natural chemical byproducts the yeast release as they consume sugar.
Exactly. In an open system, they just wash away. But in a closed loop, they accumulate. If the concentration gets too high, they become toxic and literally choke the biological process.
So it is a catch-22. You want to recycle the water to save money, but if you recycle all of it, you poison your product. How do you solve that?
You introduce a mathematically calculated release valve called a purge stream. In the digital twin, they add a flow splitter that continuously removes exactly 10% of that recycled liquid to the drain, while the other 90% loops back.
You know, it makes me think of a slightly gross but very mechanically accurate analogy.
I'm intrigued.
Imagine you are taking a bath, but you want to stay in the tub for hours on end. If you just sit there, the water eventually gets dirty and cold.
Right.
But if you open the drain just a tiny bit, letting a small trickle of dirty bathwater escape, while leaving the faucet running with a small trickle of fresh, hot water, the entire tub stays clean and warm indefinitely without you ever having to empty it completely.
That is exactly the physics of a continuous purge stream. By purging just 10%, you pull out enough toxic metabolites to keep the concentration safe. The yeast thrive.
And by recycling the other 90%, you still save a massive amount of fresh water.
It is the perfect balance of biology and economics.
It really is, and it brings our entire journey full circle today. Just to wrap up part 1 of this introductory class, we learned how bioprocess design and digital twins allow us to safely translate a lab experiment into a massive virtual factory.
We explored the various bioproducts and how the 3-level architecture keeps engineers grounded.
Right. We saw how visualizing time with Gantt charts lets us hunt down bottlenecks using staggered equipment to turn a sluggish batch process into a high-speed cycle.
We exposed the hidden realities of CapEx and OpEx and how consumables act like expensive printer ink.
And finally, we saw how engineers squeeze out maximum efficiency using virtual heat swapping and mathematically perfect recycling loops. It truly demonstrates why process simulation is the backbone of industrial engineering.
You optimize the timeline, balance the checkbook, and mitigate risks all inside a computer.
It is mind-blowing, and I want to leave you, the listener, with one final forward-looking thought to ponder. Throughout this deep dive, we've talked about how human engineers use these detailed, math-driven digital twins. But what happens when we eventually hand these simulation tools fully over to AI?
Oh, that is a huge question.
If an artificial intelligence can run millions of virtual iterations in a fraction of a second, will it soon design wildly alien, hyper-efficient manufacturing processes that a human engineer would never even dream of? Will the factors of the future even make sense to the people who build them? Something fascinating to think about until part 2. I want to express my utmost gratitude to Technologist Dr. Rama Yusvana for his enlightenment and his invaluable insights into the topics we discussed today. It was a real privilege to have you break this down for us.
The pleasure was all mine.